Hello, everyone. My name is Robert Haas. I work at EDB, and this is my talk on moving PG-based backup forward for PGCon 2022. In this talk, I'd like to tell you about some new features of PG-based backup in PostgreSQL 15. I'd like to tell you about some of the challenges that I and some of my colleagues encountered in trying to implement those features. And then I'd like to speculate a little bit about a couple of possible future features, namely parallel backup and incremental backup. So first of all, what's new in PostgreSQL 15? I think there are basically four new features here in this area that are interesting. First of all, there is server-side compression. So previously, you could tell PG-based backup that you would like it to compress your backup, but now you can either do that, or you can tell PG-based backup to ask the server to compress the backup before it is transmitted to PG-based backup. And that may be advantageous either if you just have a lot of extra CPU on the server and not much extra on the client, or more likely if you want to reduce the size of the backup before you transmit it from one machine to the other. The second new feature in this area is that PG-based backup now supports multiple compression algorithms. In previous releases, the only supported compression algorithm was gzip, but now we also support LZ4 and zstd, and those algorithms can be used either on the client side or on the server side. The third new feature is that we now have multi-threaded compression. Newer versions of the zstd library support multi-threaded compression, which is just built into the library. And you can enable that either on the client side or on the server side. And then finally, there's a new feature called backup targets. And the basic idea here is that normally when we run PG-based backup, our expectation is that the backup is going to be sent from the server to us. In other words, PG-based backup is going to receive the backup from the server. But when you use a backup target, you're directing the server to send the backup to some other location. So we'll see a couple of examples of that in just a minute. An interesting thing about this facility is that it is extensible. We have a couple of very simple backup targets which were built into the server, but additional backup targets, perhaps things like S3 or GCS, can be added to the server via loadable modules. So it'll be interesting to see what people develop. Here are some examples of how you can use these new features, and I'm just showing what the PG-based backup command line would look like here. Since this is just a test, I use the -c fast option in all of these examples to make the tests go faster. And you can see most of these options are using the tar format as well, which is what -F means. Then I give the directory where the backup ought to be stored, in this case the my backup directory. And then in the first example here, I say --compress LZ4. Now, in previous releases, the argument to --compress would have just been an integer specifying a compression level. But here you can see that I can now pass the name of a compression algorithm, and if that compression algorithm is supported, then the backup will be compressed using that algorithm. I can also specify both a compression algorithm and a level, and the next two examples show how I can do that. I can either write the name of the compression algorithm and then a colon and then the compression level, or I can spell out that the compression parameter that I am setting is specifically the compression level, as in the second example there where I say level equals 3. Then the next two examples here show how I can specify whether I would like client-side compression or server-side compression, and how I can set the number of parallel compression threads if I'm using zstandard. So in the first example here, I say that I would like zstandard compression to be performed on the client side using 4 threads. And in the second example, I also ask for 4 threads, but now I want the compression to occur on the server side. There's an option as well to compress on the server side, transmit the backup in compressed form over the network, and then decompress the backup and extract it on the client side. And it's actually really easy to do that. All you do is specify server-side compression, and then instead of asking for a tar format backup, you ask for a plain format backup. So in this next example here, I say -F_p. That means I want a plain format backup, which would normally be considered something that was incompatible with compression, but it's not really incompatible with compression if the compression is performed by the server, because the client knows how to decompress and then it can extract the backup. Then the next example here shows how we can do a backup on the server side using a backup target. So here I remove the format option from the command line, and I also have to remove the output directory option, so no -D my backup in this case. And I do also need to set the wall method to something other than the default of stream. So here I've supplied -X fetch. And then I add the --target option, and the argument to the --target option is the name of the target that I would like to use. So in this case, I've selected the server target. And then I can write a colon and then an argument to that backup target. So here the argument to the server target is a path name. And that will cause the server to write out the backup into the directory that I have specified. And the backup will be in tar format, or in this case, in gzip compressed tar format. And then in the last example here, I show how you might use a custom backup target. Now, this is a hypothetical example because I haven't written an S3 backup target, and as far as I know, no one else has done that yet either. But this is how it would be used if it existed, perhaps. Here I specify that the target I'd like to use is called S3, and then the argument to that target is, I'm supposing here that it is a bucket name and then a slash and then a bucket path, but really the interpretation of everything after the colon there would be up to whoever writes this backup target or any other backup target that we might have in the future. Here are some benchmarking results that show the effect of using server-side compression. EDB has some on-premises hardware that I was able to use to test this. Thank you to EDB for providing access to that hardware. I loaded up the UK land registry database, which is about 3.8 gigabytes and has been used for other kinds of benchmarking and testing by PostgreSQL hackers in the past. In this case, the data easily fits in RAM because these machines have a lot of memory. I was also using SSD storage on both the machine that was running the server and also on the backup machine. And those two machines are on the same LAN and connected via 10 gigabit Ethernet. So everything here is pretty fast, except for the CPUs. The CPUs are a bit slower because these machines are some years old at this point, and they didn't have the fastest available CPUs at the time that we got them. But we're just interested in a relative performance comparison here, so I don't think that really matters. In the first column of the table, you can see that I tried a whole bunch of different compression methods. The three that we support, also no compression, and then zstd compression using various numbers of workers. In the second column, you can see the size of the backup that I got. And of course, it's 3.8 gigabytes when I don't compress it, because that's the size of the source data. And then all of the compression algorithms make it smaller. zstd is the most successful at compressing this particular data set, and LZ4 compresses least well. And gzip is pretty good, but not quite as good as zstd. But what's really interesting, I think, is the third column of the table, where I show the time that it takes to perform a tar format backup with each compression method. Here, gzip is the standout loser. I mean, it's really bad. Like that time to perform gzip compression is just awe-inspiringly high compared to any of the other options, or compared to no compression for that matter. The fastest compression algorithm here, the most efficient compression algorithm, is actually LZ4. You can see that the time goes from 17 seconds up to 31.5 seconds when I use LZ4 compression, but that's still lower than the single-threaded performance of either of the other two compression algorithms. And I do get a pretty substantial reduction in size for my backup by picking that algorithm. But as I add workers, zstd starts to pull into the lead because it's the only one that has the ability to use parallel workers here. And with 8 workers, I'm able to reduce the time to take this backup from 17 seconds down to just under 10 seconds, which is pretty cool. And then in the last column here, I show the time to do a plain format backup. So in this case, the server is compressing the data, and then the client is uncompressing and extracting the tar files. And you see here that compression is strictly a loss in this case, and that is because the network between these two machines is very fast. When I tried similar experiments on a slow network, then actually this idea of compressing just for transfer is quite powerful and can actually make backups quite a bit faster. But in this case, my network is very fast, so compressing and decompressing the backup is just overhead. If I use zstood with a bunch of parallel workers, it's not a whole lot of overhead, but there's just no point because my network is fast enough that I just don't need that particular technology in this case. Okay, so that's what we have. Now let me talk a little bit about how we got there and some of the challenges that we had to overcome during the implementation phase. So one problem we ran into, which wasn't a huge problem, but we did have to resolve it, is we needed to add some new options to the base_backup replication command. PostgreSQL has a separate replication command language that is mostly used for replication, as you would expect, but it's also used as the way of allowing PG-based backup to trigger a base backup on the server side. And so adding new features to PG-based backup also means, generally speaking, that you need to extend this command language, and the syntax that we had for this command wasn't as easy to extend as I thought that it should be. So I changed the syntax and reworked things a little bit in order to make it easier to do. And the basic idea here was to adopt the same strategy for flexible options lists that we have already used for a number of our other commands, a number of our SQL commands. I think explain was the first one that got this sort of syntax where you write the command name and then an opening parenthesis and then a series of comma-separated options, each of which is allowed to have a value but doesn't necessarily have to have a value. So you write a name and then maybe a value and then a comma and then the next option name and then maybe a value for that one and then another comma. And then when you get to the end of your options list, instead of the last comma, you write a closing parenthesis. So base backup now has a grammar that looks like this. It just makes it a little bit easier to plug new options in there without having problems at the grammar level. We also needed to solve a user visible syntax problem, and that one has to do with how we're going to specify the compression method and the compression options, because in previous releases there was only one available compression method and there was only one option, which was the compression level. And now we have multiple compression methods. We also have one option, namely the number of workers that can be set apart from the compression level, and we need a way to tell the server whether to perform the compression, to tell PG-based backup whether to perform the compression on the server side or on the client side. And you saw in the syntax examples that I showed a few slides ago how we solved those problems. But the syntax that we introduced here, I'm actually quite excited about. I hope other parts of PostgreSQL will adopt it because it's really quite flexible. So the compression method name is just the name. That's pretty simple. But then for the compression options, which are the part that follows the colon in the examples that I showed you previously, you can do one of two things. You can either just write a bare integer, and then that sets the compression level, or you could write a bunch of comma-separated keyword equals value pairs. Like, for example, you could write level equals 1, comma, workers equals 8. And then you would be setting the compression level to 1 and the number of workers to 8. And this will be quite easy to generalize to any other parameters we decide we want to expose to users. And both the LZ4 library and the ZStandard library have a bunch of other parameters that we could expose to users. Now, I don't really know whether it's a good idea to expose any of those parameters to users. It's probably not a good idea to expose all of those parameters. There's probably no reason to offer that much complexity, and it might cause some kind of a problem. I'm not really sure, but the nice thing is that we have the syntax here that can easily be generalized to support whatever we want to do. So we won't be bottlenecked by trying to figure out how to sandwich any new options into the syntax. We have something here that's general enough to accommodate anything that we would like to do. A third problem that we ran into was improperly terminated tar files. I actually couldn't believe my eyes when I realized how this worked in previous releases. A tar file is supposed to end in a kilobyte of null bytes. In other words, 0 bytes. And many tar implementations will tolerate tar files where that terminator is not present, but there are some that will complain. And in previous releases, the server generated a tar file that did not include those terminating null bytes, and then PG-based backup added them to the data that's sent by the server. So you had an almost complete tar file being generated on the server side, and then the client side came along and added the last little bit. And that is going to be a problem when we start to talk about features like server-side compression or backup targets. Because if the server needs to manipulate those tar files by compressing them or by sending them someplace, it needs to be sending fully complete tar files or compressing fully complete tar files and not almost a complete tar file. And the reason why it was like this in previous releases is because of the -R option to PG-based backup, which says that you would like to inject recovery configuration into your backup. And in order to do that with a tar format backup, PG-based backup needed to edit your tar file. But its capabilities for editing tar files were extremely primitive, and it couldn't cope with something complicated like handling that kilobyte of null bytes at the end of the file and adjusting the tar file and moving that terminator around. It couldn't cope. It was too dumb. So, what we ended up doing is just giving PG-based backup a proper tar parser. It is hand-coded, as is all of PostgreSQL's code for manipulating tar files. We don't rely on an external library to do that, but I basically just enhanced the code in this area along the same lines as what we're doing everywhere else in PostgreSQL for manipulating tar files. So hopefully it's no more incorrect than the code that we had previously, and maybe it's actually right. But in any case, it does seem to work, and it solves this problem. The server now properly terminates the tar files in all cases, and if the client needs to edit the tar file, then it just does the right thing with that terminator. One of the thorniest problems that we ran into in doing this project was actually in the area of progress reporting. And there's actually two kinds of progress reporting that happen when you're performing a base backup. There is some progress reporting that's done on the server side, but PG-based backup also does its own progress reporting. And that's where the problem was. If you use the --progress option, I think that's what it's called, to PG-based backup, then it prints out information about how much of the backup it has completed as it's going. But the way that it used to figure out how much of the backup had been completed is by looking at the number of data bytes that it had received. So at the beginning of the backup, it says, hey, how much data should I expect? And perhaps the server will say 3.8 gigabytes. Well, if the client has then received 1.9 gigabytes of data from the server, it will think that it's half done with the backup. But that completely breaks as soon as you introduce features like server-side compression or backup targets. Because in the case of server-side compression, the client isn't going to receive the full number of bytes that the server has, because the compression is going to reduce the amount of data that needs to be transmitted. And in the case of a backup target, the client isn't going to receive any bytes at all. They're going to be sent to some other location. So we needed to somehow revise this protocol. And basically, what I did is change things around so that now the server sends indications to the client of how much progress it thinks it has made. So now the client doesn't count the bytes it received anymore. Instead, it just pays attention to the progress messages from the server, and then it can display that progress information to the user if desired. In order to make that happen, we changed around the protocol that is used for client-server communication here a little bit. Previously, the server would basically do one copy out operation per table space, one for the main table space and then one for each user-defined table space. And now it just does a single copy out operation for the entire backup, and each copy data message, which is part of that copy out operation, begins with a 1-byte message type code. So if the message starts with N, then it's the start of a new archive. If it starts with M, then it's the start of the backup manifest. If it's D, it's data. for whichever archive we are currently processing or for the manifest. And if it starts with P, then it's a progress report. This protocol has some fringe benefits, one of which is that it allows the server to tell the client what file names to use. So if you tell PG-based backup to use some compression method that PG-based backup doesn't know anything about, but you ask for the compression to be performed by the server, PG-based backup will just forward that compression request to the server and see what happens. And the server might error out because the server might not know anything about that compression method either. But the server may also know about that compression method if, for example, it wasn't compiled into the client that you're using on this machine, but it was compiled into the server on the other machine, and the server may just start sending data back. And if it does, it will also send the appropriate file name to use. So if, for example, you don't have LZ4 support in your version of PG-based backup, you can still request LZ4 from the server, and the server will say, oh, the file name is base.tar.lz4, and then that's all the client really needs to know, as long as it's just writing out the file. If it has to extract the file for some reason, or decompress the file, I guess I should say, then it's going to fail because it doesn't understand LZ4. But as long as it's just writing the file, it doesn't need to know anything about the compression method in order to ask the server to use it. So that's a minor thing, but it gives a little bit better interoperability, I think. And then the last challenge here was composability. The PG-based backup code, especially on the server side, but to some extent also on the client side, had gotten really pretty complicated. There are actually a lot of features that are built into the base backup mechanism and a lot of things that we have to do. We have to read the source files and we have to construct a tar file out of them. We have to do progress reporting and throttling and wire protocol communication. And in the previous coding, these things were not very well separated. You would often have a single function that knew something about all of these topics. So, you would have one function for sending a file, and it would be doing the actual file I/O, and then it would jigger things around to get that into the right format for a tar file, and it would do a little bit of progress reporting and a little bit of throttling, and then it would actually build messages to send out over the wire protocol. And it just knew everything. And similarly with all of the other functions for starting and ending backups, functions for starting and ending table spaces, functions for starting and ending files. And so that made it hard to just sort of plug new features into the system. So what I did is I invented the concept of a BB sync on the server side and the very similar concept of a BB streamer on the client side. And the idea is that each type of BB sync or BB streamer knows everything relevant about a single topic and hopefully nothing about any other topic. And so what that allows you to do is it allows you to construct a pipeline. So in the example that I've shown here on the bottom of the slide, you can imagine that you read the data and then you feed it into this pipeline of 5 steps that I have here. So first it gets fed into the progress reporting stage. That does whatever it needs to do. Then it feeds it into the compression stage. That compresses the data. That feeds it into the throttling stage, which may slow things down. That feeds it into the backup targeting stage, which ships the backup off to wherever it needs to go. And then that feeds it into the client communication stage, which sends the client progress reports and whatever other data the client is expecting to receive. And with the code structured this way, all of the knowledge about any single topic is basically isolated in a bunch of functions with related names that all live in a single file, and there's no knowledge of any other topic. And when some operation isn't being performed as part of a base backup, then that stage can be just omitted from this pipeline. If we're not doing throttling, then we don't put in the throttling stage and have it do nothing. We just leave it out completely. So in the simplest case, where you're not using compression or throttling or a backup target, you'll actually only have 2 stages in this pipeline on the server side, the progress reporting stage and then the client communication stage. But as you make use of the other features that PG-based backup has, then these additional stages are inserted. And it's pretty easy to add additional stages in here. So I think now, for example, if somebody wanted to add backup encryption as a capability, it would be pretty easy to do. You would just write a new BB sync that implemented whatever you need, and then you would figure out the appropriate place to insert it into the pipeline, which I would guess would probably be right after the compression stage. So none of the other code would really need to change. None of the code for progress reporting or compression or backup targeting or client communication would be affected at all. There would be entire files that you could completely ignore. You would just need to write a new file that knew everything about how to encrypt the data. And then you would need to write a little bit of glue code to make sure that gets inserted into the pipeline at the correct point. And that would be all the work that there was to do. So I think that's kind of cool. All right, so that brings me to the end of the portion of the talk where I discuss the features that were implemented for version 15. So now I would like to speculate a little bit about the future. And first, I'd like to speculate a little bit about the possibilities for parallel backup. So as with any new feature, the first question that we should ask is, why would you want that feature? And I think the answer is that we'd always like our backups to be faster. We do have parallelism from a certain point of view in version 15 because, compression is a very CPU intensive operation, as you saw from the previous slides. And if you use Z standard, then you can do that part in parallel. But there's a bunch of other things that a backup does as well. And it might seem like a good idea to use multiple processes or threads to speed up that other stuff as well. The problem, though, is that that might not actually work. A lot of the work that is performed during a backup is I/O. And there are some situations where using multiple processes or multiple threads to perform I/O at the same time is faster. But there are also a lot of cases where it's the same speed, and there are a significant number of cases where it's actually a lot slower. So that's a problem. There's no point in implementing parallel backup if it's not going to make the backups get faster, or if it's only going to do so in certain niche circumstances. And the other problem here is that it might not be the best way to make backups faster. I've been doing some testing of the new code, and I think that we've still got some bottlenecks. I don't think we're getting as much performance with a single thread on each side as we potentially can. It looks to me like PG-based backup, the client in particular, is probably slower than it needs to be. And I haven't completely understood everything that's going on there, but I think there are opportunities to squeeze more performance out of the system without doing anything to make it more complicated. Just by writing better code, I think we may be able to get some efficiency out of the system. So I think more research is needed here. I definitely don't rule out the possibility that in the future, we're going to find that there are cases where parallelism is the only way to make gains. But I'm not 100% sure that we will. I think that when you have an operation that's doing this much I/O, probably the most important thing is to do that I/O as efficiently as you possibly can. And if you do that, hopefully you don't have a whole lot of CPU consumption, and therefore hopefully you don't need a whole lot of parallelism. But there may be cases. There may be cases where the maximum bandwidth for a single network connection is limited, but with multiple network connections, you can achieve more bandwidth. That's not the case on a normal network, but it can be the case, for example, in an AWS environment. There might also be cases where you can get speed ups with I/O by using multiple worker processes to help you with that. So anyway, more research is needed here. I have not ruled out the possibility that this might be a good idea, but I think, in my opinion, there are other topics to explore first that may deliver more benefit with less work. The other feature I wanted to talk about a little bit is incremental backup, which I think is a really, really interesting idea. So an incremental backup would mean that you perform a base backup, but you don't get all of the bits that exist on the server. You only get the parts of the data that have changed rather since the last time you took a backup. So anything that's unchanged is omitted from the backup, and anything that has changed is included in the backup. And then you have some method of reassembling everything when you actually want to run the database. I think it is pretty clear why we might want to have incremental backup, and that is because it can drastically reduce the total amount of work that is needed in order to complete the backup. So in that sense, it's very different from parallel backup. because parallel backup just tries to get the work done faster, but it doesn't save you anything. Incremental backup does save you something, and potentially it saves you quite a lot. If you do a full backup on Monday and then you do an incremental backup on Tuesday, it's possible that like only 1% of your database has changed. And if that's the case, and you have an efficient way to identify which 1% of the database has been changed, you can complete that backup like 100 times faster, which is huge. And it's not just that the backup finishes in 100 times less time. It's also that you basically do 100 times less work. So you have 100 times less CPU, which probably doesn't matter, and 100 times less network transfer, which may matter, and 100 times smaller storage requirement, which might also matter. So I think incremental backup is a really, really interesting feature idea. But there is one big sticking point, which is how do you figure out what part of the database has actually changed since the previous backup? I have thought of or heard other people propose at least 5 different approaches to this problem. One idea is to use file timestamps. So if the full backup was done on Monday and now you're doing an incremental relative to that full backup on Tuesday, and you see that the data file hasn't been changed since Sunday, then you say, okay, well, that doesn't need to be included in the incremental backup because the file modification timestamp is too old. A second possible approach is to do checksums. You could checksum entire files, you could checksum individual blocks within files, and you could do that on the running server and also on the previous backup, and you could compare the checksums. And you could say, well, if the checksums match, then I'm not going to include the block in the backup or the file. And if the checksums do not match, then I will include that file or block in the backup. And this is, for example, an approach that has been used very successfully by rsync. A third possible approach is to rely on the block LSNs. Now, LSN stands for log sequence number, and it's basically the position inside the write-ahead log where a particular record was written. And every time we write a record to the write-ahead log that causes some blocks to be modified, we also stamp those blocks with the LSN of the wall record that made those changes. So if we know the LSN at which the previous backup started, and we do because we already preserved that information, then we could go and through the cluster and look for blocks which have an LSN that is newer than that value. And any blocks we find have definitely been modified since the previous backup began. And so we could include all of those in our incremental backup and exclude everything else. A fourth approach is instead of looking at the LSNs on the blocks, we could look directly at the wall. And we could figure out from the wall, from the write-ahead log, which blocks have been changed since the previous backup. And then whatever blocks have been changed, we include those in the backup, and the rest we exclude. And a fifth idea is to have the server do some sort of tracking and figure this out for us. The server could track which blocks have been modified since the last full backup, or even exactly when they've been modified. And this could be done on a block level, or it could be done for ranges of blocks. It could be done for entire files. There are a few different ways of doing this. But unfortunately, all of these strategies have problems, and in my opinion, all of them have fairly serious problems. The problem with file timestamps is that we really can't tell whether the system clock had been changed. It probably hasn't been. In 2022, most people are going to have reliable time synchronization, and they're not going to go fiddling around with the system clock by hand. But they could. You could set the timestamp on the system backwards a week, change some data in the database. The file modification timestamps are now going to be old, even though the data is new. Then you set the clock forward again, you take an incremental backup, and you get the wrong answer. In terms of using checksums on files or blocks, you have to read your entire backup so that you can compute checksums on those files or the blocks within those files, or maybe that work can be done in advance. And then it seems like you also have to read the entire running database to get the current checksums for those files or blocks, and then you have to perform comparisons between the two. So it feels like there's a lot of work that's required here. There's also at least a theoretical possibility of collision. What if two blocks have different contents, but just by bad luck, they happen to have the same checksum? Then you would omit something from the backup which ought to have been included. The block LSN approach has a similar problem with needing to do a lot of work. It doesn't require going through the entire backup, but you do have to go through the entire running database and figure out which blocks have LSNs that are newer than the start of the previous backup. And so that's a lot of work. But there's an even more serious problem, which is that sometimes we copy files around without actually changing the LSNs that exist inside those files. And so then you have new data that needs to be backed up, but the LSNs of those blocks are old because the files were just flat copied and they weren't copied in a way that causes the LSN to change. In terms of extracting block references from the wall, it's a complex piece of new infrastructure. You have to build a whole bunch of stuff in order to make this work. And another problem with it is it adds some administrative complexity. In order to take an incremental backup, you're going to need to have all of the wall since the prior backup on which that incremental backup is to be based. Or maybe you don't need to have all of the wall. Maybe you could just have a small summary of the wall. I think that's probably the more practical approach here, where you would summarize the wall, and instead of having all of the wall, which is quite big, you would create some small summary files that contain just the information that would be needed for this purpose. Those would be a small fraction of the size of the original files, and then you would keep those files around for as long as you need them in order to be able to perform your incremental backups. But there's still some administrative complexity here because only the system administrator will know when those files can be removed. And maybe they'll get confused and not be sure when to remove those files. So there are some issues there, I think. And then the last approach of having the server do tracking of which blocks have been modified or which files have been modified or however you want to do it, that's also a complex piece of new infrastructure. And I think that creates some extra work for the server that probably has to be done in the foreground. I think that an approach like this, in order to work well, would really need to do the tracking at the same moment that the changes are made. You could examine the wall later, but I think with this kind of approach, you actually need to do the tracking at the same time that you perform the operation. And it seems like you probably need to make it crash safe as well. So the way that this works would need to be integrated carefully with the write-ahead logging system, which seems like it might have a little bit of performance overhead or at least be a little bit complex. So everybody is going to have their own opinion about what the right thing to do is here, and none of those opinions are right or wrong. People just think different things. My personal opinion is that I really like the approach of either using the block LSNs or of extracting block references from the write-ahead log, or maybe some combination of the two in different situations. The reason I really like those approaches is that they enable us to rely on existing PostgreSQL infrastructure. And it's PostgreSQL infrastructure which is really battle tested. I mean, I'm not here to say that there are no remaining bugs in the write-ahead logging system, but there's a lot of people using the write-ahead logging system every day. It's used for standbys. It's used for crash recovery. We do get regular reports of bugs in the system, and those get fixed. And so that system has just, gotten better and better and better over the years. And in general, it's pretty solid, which in my opinion makes it a good basis for building new things. If we create something that is separate from that system, and that's a completely new piece of infrastructure, it's going to have its own set of bugs. And that's not great. It seems better to me if we can find a way of leveraging the information that we already have about when blocks have been modified rather than coming up with some new way of figuring that out. It seems more efficient, but more importantly, to me, it seems safer. So I actually went as far as to write a rough prototype. It just took a few days. It was based on block LSNs, and I was able to fix some of the problems with flat copied files and old LSNs, but then I realized there were some problems that I could not fix. So I've had to abandon that effort for now. I'm thinking about some possibilities for how I could get around those issues and maybe make that approach actually be safe. But I think there is a possibility here that if we can agree on an approach and the approach is not too onerous, maybe something could actually come together here in a reasonable period of time, which would be really cool. So just a few concluding thoughts here. I do think it's really exciting to see PG-based backup developing some new useful features, and I think it would be good if it got a few more. I'm probably going to work on that myself, but I also think it's great if other people work on it. I'm not here to say that it's great if I add features to PG-based backup. I'm here to say that it's good if features get added to PG-based backup. I don't think that we are anywhere close to getting to a point where everything about backup and restore is handled in core. I don't see that day coming anytime soon because there are so many things which you're going to want your backup tool to do, and we are so far from being able to do all of those things in core. So I do not think that out of core backup tools are going to go away anytime soon, and I think in many ways that's a good thing because those out of core backup tools can iterate very rapidly. They're not bound to the PostgreSQL release cycle, and they don't need to get consensus between a large group of people about what we ought to do. The author of each individual tool can make whatever modifications they like, and that's great. So I do like the fact that those tools exist, but I don't like the fact that you're so dependent on them for so many use cases. It's almost impossible to do any kind of backups of the server at all in a really serious way without relying on one of those third-party tools. And that I don't think is good. I think that we, at the very least, need a robust set of facilities built into core that cover basic use cases. And then maybe if you want more advanced things, you can go to some of the tools, hopefully leveraging as much of that in-core infrastructure as possible rather than inventing everything all over again. So I think it's important that whatever goes into core can integrate well with these backup tools as people create them. And I think it's also important that what goes into core is complete enough that you can really use PostgreSQL without having to necessarily go and download a whole bunch of other software from the internet. Obviously, different people are going to have different opinions about this, and that's totally fine. That's just my opinion. But I hope this presentation was useful to you. I hope that you learned something and that some of these features will be useful to you. And so thanks for watching.